So, next speaker is by myself. Today I'm going to talk about the hydration structure of the intermediate water in biomaterials. This polymer, PMEA, already discussed by the Professor Tanaka. This polymer contains a lot of intermediate water investigated by using the mid-infrared spectroscopy. As Professor Tanaka already said, the intermediate water was found by the thermal analysis below 0 degrees Celsius. But today I'm going to talk about this type of water investigated by the spectroscopy around room temperature. Both near-infrared spectroscopy and mid-infrared spectroscopy are promising tool for the investigation of the hydrogen bond system, including the water and alcohol and so on. This figure shows the absorption coefficient spectrum in the mid-infrared and near-infrared region. In the mid-infrared region, the absorption coefficient is very large. And therefore, however, in the case of near-infrared region, the absorption coefficient becomes smaller. Therefore, we can obtain the near-infrared spectrum using such a cuvette cell. In contrast, in the mid-infrared region, due to the intense absorption coefficient, we need more careful experiment using like this cell. However, we can obtain not only the OH vibration, but also other functional groups can be obtained by the mid-infrared spectroscopy. This figure shows the mid-infrared spectra in the OH stretching region of methanol dissolved in a carbon tetrachloride. This line represents the spectrum of methanol dissolved in a carbon tetrachloride such a low concentration of 0.1%. It means that one methanol molecule was surrounded by the 999 carbon tetrachloride solvent. Now we can identify very sharp and intense absorption can be identified such a higher wave number at 3663 wave numbers. With increasing the methanol concentration, like 1% and 10%, we can identify two contributions located around 3520 and 3334 wave numbers. These two broad features are arising from the dimer or aggregate structure. It means that in the OH stretching region, the hydrogen bond structure can be seen as a larger hydrogen bond structure can be observed as a lower wave number contribution, or a bulk solution becomes more broader. Not only OH stretching vibration, but also other types of functional group can be observed by the mid-infrared spectroscopy. Now we can consider such a Lewis acid or Lewis basis, because this is an electron donor. And now we consider the typical hydrogen bond system using the methanol and methyl acetate, typical carbon group, using the model compound of the PMEA water system. This figure shows the mixture of methanol and methyl acetate. Bottom one is a spectrum of methanol in carbon tetrachloride, about 1% already shown before. And this one is a free, and this is a dimer, and this is an aggregate OH. With increasing the concentration of methyl acetate, new bands appear at this vibration frequency C at 3572 wave numbers. This is the evidence of the COOH hydrogen bonds. And this one is band C is a first overtone of the CO vibration. And in the case of CO stretching region, this one, band T, is a CO double bond band. With increasing the concentration of methanol in the solution, shoulder peak appears at 1733. This one is the evidence of the hydrogen bonded CO. Like that, we can obtain not only OH vibration, but also the counter chemical can be obtained by the mid-infrared spectroscopy. Today I'm going to talk about the result of the PMEA, already described by the Professor Tanaka. And he said this polymer contains three types of water. One is non-freezing water. This water has a strong interaction with the polymer chain because this water cannot crystallize around minus 100 degrees Celsius. Free water or freezing water have the bulk-like structure, and Professor Tanaka said that it is very interesting. Freezing bound water was found by the thermal analysis, and the content of the freezing bound water or intermediate water is dominant. Today I'm going to talk about the hydration structure of each water. How can we investigate it? Using the in situ attenuated total reflection infrared spectroscopy. In this case, a thick polymer film compared to the penetration dips generated as the prism polymer interface was prepared by the solvent casting method. In this case, only solving water molecules into the polymer matrix, excluding the bulk water contacting with the surface of the polymer film, was detected because in this case, thickness of the film is enough thicker than the penetration dips. By using this method, we obtain such a spectra. These are the ATR spectra of PMEA. Blue one is the spectrum of PMEA measured under the dried condition using the nitrogen gas flow into the cell. And red one is a hydrated PMEA. This spectrum was obtained after injected the water into the cell. I should say again, these are the typical evidence of the OH stretching and OH deformation arising from water molecules. It's coming only solved water, excluding the bulk water. And also, decrease of the polymer bands are also observed. These are the evidence of the swelling of the film because decrease of the polymer chain density in a unit volume becomes larger, so the decrease is the evidence of the swelling of the film. And then we obtain the time-dependent spectra during the sorption process of water into the polymer matrix. At the 0 second, we obtain the reference spectrum, and then enough dry sample, and then the liquid water was injected into the cell, and this one gradually increasing the OH stretching and OH bending mode can be seen. This is evidence of the sorption of water, as well as decreasing of the polymer band represents the swelling of the polymer film. However, it is very interesting. This band located at 70-20, this is a typical carbonyl band, initially increases before the gradual increase of the water band. This is the evidence of the initially hydrated to the carbonyl group, like that. We can obtain different functional group in the fingerprint region. So how can we interpret such the broad and different spectral shape in the OH stretching region? It is very interesting. At the initial stage, the higher wave number contribution is dominant, while after the late stage, the lower wave number contribution is dominant. We can identify this is a typical variation in the water structure as a function of time during the sorption process into the polymer matrix. And we apply multivariate curve resolution for the time-dependent spectra. I already said there are three types of water in the PMEA matrix. One is non-freezing water, and free water, and intermediate water. And assuming the three contributions, we successfully obtain the three different waveforms in the OH stretching region, as well as the time dependence of the intensity. The non-freezing water has a higher wave number contribution like the methanol-methyl acetate mixture. And free water shows this spectral shape very similar to the bulk water. And it is very interesting. at the intermediate water shows this spectral shape having the peak maximum around 3400 wave number. This vibration frequency is lower than the non-freezing but higher than the free water. And this is the time dependence. Non-freezing water initially appears during the sorption process. Free water gradually increases intensity. The intermediate water had the intermediate time domain between the non-freezing and free water. So how can we interpret the hydration structure? We carefully check the fingerprint region. So first of all, we check the sea obstructing vibration region. We can find this sigmoidal spectral shape. We assume two contributions. This is a plot of the intensity assuming the hydrogen bonded CO and free CO. Negatively increase of the free CO represents the swelling of the polymer, but hydrogen bonded CO initially appear like non-freezing water. Therefore, we conclude non-freezing water hydrated the carbonyl group in the polymer. And we assume this area intensity is calculated by the area intensity, and this ratio becomes 0.245. And the content of non-freezing water already obtained by the thermal analysis, and then the number of hydration of non-freezing water is calculated about 0.132. Using two values, we calculated the number of water molecules hydrated to 1 carbonyl or 2 carbonyls. Using this equation, finally we obtain almost all water molecules, non-freezing water, about 86% have such structure, means like a bridge structure, one water molecule hydrated 2 carbonyls. And we found a typical peak position shift in this band around the methoxy moiety band has a large peak position shift as a function of time. And this time domain is more or less similar to the time region of the intermediate water sorption. Therefore, we conclude that intermediate water has an interaction with the methoxy moiety from this result. And I also measure not only PMEA, but also the analogous polymer having the different carbon number in the main chain. These are the mid-infrared spectra having the different carbon number 4, 5, 7, 8 in the main chain. And we obtain the sorption process into the different carbon number in the main chain polymers. And the obtained spectra were analyzed by the MCR. Assuming the 2 component or 3 component in the water bands, it becomes, at the carbon number of 2 means the PMEA. In this case, 3 contribution can be clearly observed. In the case of 4 and 5, similar to the PMEA. However, a large number of carbon in the main chain, and the spectral shape becomes almost 2 components. It means that a third contribution becomes similar to the second contribution. It means more poor intermediate water content in the such the longer main chain. Also, the MCR result of the intensity of the third component becomes 0 in the case of longer main chain. It means more poor intermediate water content at the lower carbon number polymer. Also, the evidence of the hydration to the methoxy moiety obtained by this band position shift also becomes band position shift becomes smaller with increasing the carbon number. It means such the higher carbon into the main chain has less intermediate water. This is a conclusion. Non-freezing water, this water soaked in the initial stage of the sorption And this water has a strong interaction with the polymer chain, like this. One water molecule hydrated to two carbonyls. Therefore, this type of water hardly crystallizes, although the temperature is around minus 100 degrees Celsius. The free water, so it's at the final stage of the sorption process, and this water has a similar spectral shape with the bulk water. And it is interesting. We clearly find the evidence of the freezing bound water or intermediate water. This water soaks at the intermediate stage between the non-freezing and freezing water. And this type of water has a smaller water cluster on the mesocene moiety because the vibration frequency is lower than the non-freezing but higher than the free water. My talk today is that all. Thank you for your attention. So, question, comments? Yeah.
I noticed, excuse me, I noticed that the time course of buildup of intermediate water was a few seconds, a few minutes, I think, 3, 4, 5 minutes. And that's very similar to the easy water that we found. It takes, typically next to some hydrophilic surface, it takes a few minutes for it to build up. And I wonder, I'm not sure if you're aware of the easy water, which also excludes. I wonder if you think there's any similarity between the two, or I'm going to be talking about that today if you're not familiar. I'm just wondering if you did know about the easy water, whether you think there's a correspondence between the two.
Thank you very much. But it depends on the materials. But the intermediate water appears, the intermediate time course after the non-freezing, before the freezing, free water. Yes, thank you for your comment. Any other question or comments? Okay, thank you very much. I'll move to the next talk.